Morning, calculus students. So today I want to talk about 7.8, improper integral. So in this section we will learn how to solve definite integral, where the interval is infinite and where the function has an infinite discontinuity. Okay, so we'll take a look at the slides. So let's say that f has an infinite discontinuity in the closed interval a to b. So this one, the integral is called an improper integral, for example, like exponential growth, decay functions. So once you try to find the area under the curve, because the tail, it goes all the way to getting close to 0 or getting close to the horizontal asymptote. So you see that. Or here's another example. So under the curve, y equals 1 over x squared, which is the graph I'm going to show you later. And this one, we do know that finding the area above the x-axis to the right of the line x equals 1. So let's take a look at the graph here. So let's say that we want to integrate that from 1 all the way to t, and we don't know where t stops, because this one it goes all the way to infinity. Okay, so integral from 1 to t, 1 over x squared dx indicator. So integrating it, so we do have negative 1 over x for the functions, and then the boundary 1 to t. So using that f of tc part 2, we do have 1 minus 1 over t. And notice that a of t, it's less than 1. And no matter how large t is chosen. Okay? Well, the thing is that, you'll see that in a minute. So how do we get the approximation for this area? So the way to do it, we just want to put in the limit. So anytime they deal with the improper integral, so since t goes all the way to infinity, so we put in the limit, t goes to infinity. And then we just find the limit for the function after the integral, after the integration. So it's 1 minus 1 over t as limit as t approaches infinity. So t goes to infinity, so 1 over infinity, that's zeros. So 1 minus 0, then that's 1. So the area of the curve, so you may notice that cannot be greater than 1. So if that stop here at 2, so it's about 1/2. Stop here at 3, so 2/3. Stop here at 5, then that'd be 4/5. And then all the way to infinity, then that'd be 1. So we say that the area of an infinite region S is equal to 1, and we write it like this. Okay, so integral from 1 to infinity, 1 over x squared dx. So that equals the limit. T goes to infinity. Integral from 1 to t, 1 over x squared dx equals 1. Okay, so now we'll look at that, some of the examples. So this one gives you the definition of the improper integral technique. So if integral from a to t, as you may notice, a is a constant, f of x dx exists. For every number, t must be greater than or equals a. Therefore, the integral from a to infinity, f of x dx, so that equals the limit as t approaches infinity of the integral from a to t, f of x dx. So provide this limit exists as a finite number. If the number exists, that means it's going to be the exact value. That's what a finite number is. Okay? If that's a negative infinity, so same kind of situations, but this time t must be less than or equals a. So the improper integrals, integral from a to infinity, f of x dx, and integral from negative infinity to b, f of x dx, I'll call conversion. If the corresponding limit exists, conversion, that means the finite sum can be found. And divergent if the limit does not exist, because sometimes it goes all the way to infinity. And also, another definition for this, integral from negative infinity to infinity, f of x dx, can be written as integral from negative infinity to a constant a. So a, you probably want to say it's a breaking point, or it's the neutral number, f of x dx, and plus integral from a to infinity, f of x dx. So that means we can split it into two parts, the first part and the second part. So any real number, a, can be used. Okay, so now we'll take a look at that, the example in a minute. So this one just shows the example for the graph of the improper integral. So type 1. So f of x is greater than or equal to 0. So greater than or equal to 0. So that means it's right above the x-axis. And this one, the tail is getting very close to 0. So then we define the area of the region. So area such equals x comma y such that x is greater than or equals a, and 0 it's less than or equals y, and it's less than or equal to f of x in the figure as area of the functions, the integral from a to infinity f of x dx. Again, we need to take the limit as t approaches infinity. So determine whether the integrals of 1 over infinity, 1 over x dx is convergent or divergent. Again, convergent, that means the limit can be found. Divergent, the limit cannot be found. So let's try to do that. So we integrate it. So we do have natural log of absolute value of x. Again, this one, it goes all the way from 1 to t, and using FTC part 2. So we do have natural log of t minus natural log of 1. And you may notice that natural log of 1 is nothing. And now we want to put in t equals infinity. So natural log of infinity, such as infinity. So the limit does not exist for a finite number as a finite number. So the integral is divergent. So this one is not the exact value, infinity. It can be 100, 1,000. It can be 1 million, 1 trillion, or 1 gajillion. It's a very big number. It goes on forever. So this one, it's considered a divergent integral. So let's compare the results example 1 with the examples at the beginning of the sections. So integral from 1 to infinity, 1 over x squared dx. So this one converges. And the other one is diverges, because that's only 1 over x. So geometrically, this means the following. Okay. So as you can see the curve right here, they're pretty similar, and they're both going to infinity. But for 1 over x squared, the limit exists. But for the other one, the limit does not exist. Okay, so this one we need to focus on a little bit more, and we'll find out the reason why. So note that both 1 over x squared and 1 over x approaches 0 as x goes to infinity, but 1 over x squared approaches faster than 1 over x. Okay, it's about the rate of change for the functions. It approaches faster than 1 over x. So now here's another one. So let's try to use the improper integral techniques for this. So integrating it from negative infinity to 0. So we do have the limit. So t goes to negative infinity. Integral from t to 0, x e to the power of x dx. And as you may notice that we have to use the integrated by part technique for this. So using that, so we do have uv, and then du and v, and then integrate that t, integral from t to 0, e to the power of x dx. So we do have the exact same thing, e to the power of x. And then plug in the boundary, so ftc part 2. So here's what we come up with. And negative t, e to the power of t, minus f of tc part 2. So we got 1 plus e to the power of t. And take the limit as t goes to negative infinity. So take the limit, so we do have 1 over negative e to the power of negative infinity, which is positive infinity. Okay, so we do have limit t goes to negative infinity of the functions, negative e to the power of t. Just once you flip it over. And then plug in negative infinity, so we do have 1 over negative e to the power of infinity, well, which is getting close to what? 1 over negative infinity. It's 0. It's getting very small. So it's a constant. So that part right there, that's zeros. So here's another part which is 0. But the one here, if you try to find the limit, it's negative 1. So that means the area for this curve, it's negative 1. Well, the reason why that is because that it's underneath the x-axis. So here's another way. Here's another one that you want to evaluate using the definition that we talked about earlier. So for negative infinity to infinity, we want to use zeros as a neutral number to separate the integral. So we got the first part of the integral, negative infinity to 0. The other part of the integral, 0 to infinity. So separate them out and then integrating each integral here. So we do have inverse of tangent of x, ftc part 2, and then plug in infinity. So we do have inverse of tangent of infinity, which is pi over 2, and then inverse of tangent of negative infinity, then that'll be negative pi over 2. So 0 minus negative pi over 2, then that'll be pi over 2. And then eventually we want to combine them together. So it's pi. So as 1 over 1 plus x squared is greater than 0, the given improper integral can be interpreted as the area of an infinite region that lies under the curve. So this one, as you can see, that's like a bell curve. So for those who are taking stats, or for those who took stat before, it's a normal distribution curve. If you try to separate this out, so we do have the area of the left-hand side, and which is symmetrical to the area of the right-hand side. So once you combine both sides area, so totally it's what? Pi. So for what values of p is the integral from 1 to infinity, 1 over x to the power of p, dx divergent. So according to the previous example, if p equals 1 or it's less than 1, so the integral would be considered divergent. But anytime p is greater than 1, so the integral would be considered convergent. So we'll take a look at that. So the way that we did it, so just do it in general. So x to the power of negative p using the power rule, and then f of tc part 2, and then plug in t equals infinity. So here's what we can find. So t goes to infinity, so t to the power of infinity minus 1, then that'll be infinity. So 1 over t to the power of p minus 1, then that'll be 0. Okay? And therefore, integral from 1 to infinity, 1 over x to the power of p dx. So that equals 1 over p minus 1 if p is greater than 1. So that the integral converges. However, if p is less than 1, then p minus 1 is less than 0. If p minus 1 is less than 0, so that means the limit for this one, as p goes to negative infinity, so the whole thing goes to infinity. Okay? So as p goes to negative infinity, then the whole thing goes to positive infinity. So thus, the integral diverges. So again, so anytime that if you see that p is greater than 1, so that means the improper integral convergent. It's convergent. And then if you see that the value of p is less than or equals 1, so that means the integral, the improper integral, it's divergent. So suppose that f is the positive continuous function defined on the finite interval from a to b, but has a vertical asymptote at b. That's why b is not included. So this continuous integrand, let S be the unbounded region under the graph of f and above the x-axis between a and b. For type 1 integral, the region extends indefinitely in the horizontal direction. And here's the region is finite in the vertical direction. So like this. So the area of part of S between a and t, the shaded region, is given like this. Integral from a to t, f of x dx. This continuous integrand, if it happens that a of t approaches a definite number, a, as t approaches b from the left-hand side, then we say that the area of the region S is the area, and we write it like this. One side the limit. And we use the equation to define an improper integral for type 2, even when f is not a positive function, no matter what type of discontinuity f has at b. Okay. So now we'll look at that the example in a minute. So this one is just using that the one-sided limit. Okay, so this one is just getting a little bit more in depth regarding the divergent convergent for the improper integral. We'll get back to this one once we get into the sequences in series, because this one is considered one of those tests for sequences in series. So there's no need to continue with the rest of this here, but well, here's the last example. So integral from 2 to 5, so 1 over square root of x minus 2 dx. A lot of people probably try to do it this way. So if you just plug in 2 right here, then the integrand would be considered undefined because that the denominator cannot be 0. So this one you probably want to say that is from 2 all the way to 5, but 2 is not included. You can say that's getting close to 2 from the right hand side, but you cannot say that it appears at 2. So that's why I put a limit as t approaches 2 from the right hand side. So once you integrate it, so we do have 2 square root of x minus 2 from t to 5. Again, t is getting close to 2 from the right hand side. Once again, if you plug in 2 here exactly, so the original integrand would be considered undefined. If that's undefined, so it's no purpose of doing the integration. So now we integrate it, and then using that f of tc part 2, plug in the limit, plugging that the value of t from the right hand side, so t is getting close to 2 from the right. So here's what we found, it's 2 root 3. The reason why that I can put in 2 for this one here, because that there's no restriction. So this part of the limit here, it turns out to be 0. So what's left is just 2 root 3. So thus, the given improper integral, it's conversion. So here's the graph interpretation. And determine whether that integral from 0 to power 2 secant of x dx converges or diverges. So one thing that we notice, secant of x, as x goes to power 2 from the left hand side, is considered infinity, according to the parent graph of secant. So just basically integrate it, part 2 of ftc, so here's what we found, and then plugging that power 2 from the left hand side. So this part, it's actually infinity. This part right here, it's also infinity. Infinity plus infinity, that's another infinity. Minus zeros, then that'd be infinity. Evaluate integral from 0 to 3 dx over x minus 1 if possible. Okay, so we separate them out. So from 0 to 3, so start off from 0 to 1, because at 1 here, it's considered undefined. So you probably want to say that t goes to 1 from the left. Okay, so we're integrating it. Part 2 of ftc. So 1 from the left hand side. So we found that it's negative infinity for the limit. So natural log of absolute value of negative 1 is 0. So for this one, you want to put in 1 from the left. So you want to put in 0.99999. So natural log of 0.00001, it's about negative infinity according to the parent graph of natural log. Okay, so integral from 0 to 1 dx over x minus 1, it's divergent. So that implies integral from 0 to 3 dx over x minus 1, it's divergent. So again, do not worry about the last two examples here. So this one is more continuation with sequences in series once we get into that chapter. Okay, so thank you for watching the video today. So I'll see you guys next time.